Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
Today I'd like to talk a little bit about the physics that goes behind music. But of course, in order to say something about the physics behind music, I had to say something about what is music. So if you go on Wikipedia and you sort of search for music, you'll find out literally the word music means the art of the muses. And then you say, well, what are the muses? Turns out the muses are 9 Greek goddesses of literature, science, and the arts. Literature, science, and the arts. That does sound kind of familiar, actually. Yeah. But the implication here is that art, science, music is all sort of intertwined. And so I would like to get across the idea that there is physics in music, and perhaps there's even a little bit of music in physics. Well, music, if you try to define what is music, it's one of these things, I know, I listen to music, I hear it, I understand what music is, but if you really try to push something, what is music? Well, it's not always that easy to give a definition, but if you take a sort of a low-level point of view, you say, well, music is sort of the art of arranging tones to make pleasing sounds. You know, not everyone's definition of pleasing sounds might be the same, it can definitely change, but we know we've enjoyed music, or our ancestors have enjoyed music since at least the time of the ancient Greeks, and of course, much earlier than that. Pleasing music versus something like noise, might be a little bit culturally dependent, also might depend on, what era or what time you're in. Nevertheless, there's a sort of a good sense of, well, music is a sequence of notes, it's a melody, it's a tune, it's something like that. So if you think about what is music, one sense is to say there's some structure to it. It's not just random tones or random notes. There's usually a melody, and the melody is what you might whistle, what you might sing. The melody is sometimes thought of as the horizontal component of music. So if I have a little music over here, and I read the music from left to right, basically it's what notes go in sequence in time. That is sort of the melody. The harmony is sometimes thought of as the vertical component of music. And of course there's a little bit more to it. There's rhythm, there's what notes you play, how fast you play, do you play loud and soft, sort of dynamics. Now what I've done over here is to give you sort of what you might think of as music, but is it really music? Well, it's not really music, this is how it's written. Music is actually what we hear. And so what is it? Is, I actually have a trusty piano over here, I can actually play the melody. Along with the harmony, and I can put everything together. When you listen to something, what are you hearing? Is you're hearing sound. So I want to start today a little bit by talking about sound. In order to understand what music is, we should also understand what is sound. Sound, I think everyone will know, you say sound is sound waves. Well, what are sound waves? Sound waves, I'm talking to you right now, and of course it's being amplified through the speakers, but if you ignore that for a little bit moment, sound is something that's coming out of my mouth and it travels to your ears. So the nature of sound waves is something we've learned about, turns out it's basically pressure disturbances in the air. So as I speak, my vocal folds are going, and I'm sort of oscillating or vibrating the air a little bit. I'm pushing a little bit of pressure through the air. If you abstract that a little bit, the pressure waves are actually doing something. They are carrying energy and information, basically from my mouth to your ears. So I can think about sound waves, or waves in general, as a disturbance that sort of transmits energy from one place to another. I should be a little bit cautious about that statement, and the idea is I say I have sort of pressure disturbances. The air molecules in this room are vibrating as I am talking, but the air molecules themselves, if I actually look at one molecule, is not actually going from my mouth into your ear. I'm not sort of blowing wind at you when I'm speaking. And in fact, that's a very, very good thing. You wouldn't want that. So there are pressure disturbances that somehow transmitting energy, transmitting speech, transmitting music from one place to another, but it's not the same as sort of blowing air molecules from one place to the other. So basically, a given air molecule just sort of vibrates around like that. As I speak, air is vibrating here, vibrating here, vibrating here into sort of a wave pattern. Well, how do we really know that sound is being carried through the air? Here is a bell inside a jar. Now, actually, since we have such a large crowd over here, there's a little microphone inside this jar that's about 4 inches away from the bell. The bell is ringing. The sound wave goes through the air, picks up by the microphone, and we can hear it like this. Now, if I remove the air by pumping it into a vacuum, let's see what happens. It's a pretty big jar, so it takes a little bit of time to pump it down. See, it's getting a little bit quieter, quieter. I want to show you that the light bulb is on over here. The light bulb is connected directly to the bell. So the bell is ringing, it's still getting power. You can still barely hear it ringing, at least I can. But it's definitely getting very quiet. And if I wait long enough, it can actually more or less just disappear. So when I've removed the air, you don't hear the sound anymore. Just a little bit. If I put the air back in, well, of course, you're going to hear it again. Now, you're going to also hear the air rushing into the jar. Microphone picks up just about everything. This is to show you there's no tricks. The bell is still ringing. There it is. No air means no sound. And on that note, I want to talk about science fiction explosions. What's unrealistic about that? Yeah. So we know sound is waves that are carried through air. We want to understand some of the properties of sound. And it turns out, of course, a wave has a given speed associated with it. Sound waves are not instantaneous. It takes a little bit of time for sound to go from one place to another, as any wave will do. Of course, with air pressure and sound waves, you can't really see the air. Nevertheless, I can demonstrate a little bit instead of using air. I have a nice rope over here. And if I send a little pulse on the rope, you can see the wave. It's really fun because you can actually see it bouncing back and forth a little bit. If I have a pulse over here, it travels, of course, from left to right. And then it bounces against the wall and it comes back. The other thing to notice, of course, is there's a little red tape or red flag in the middle. The wave is moving reasonably fast from left to right. The flag bounces up and down a little bit, but the flag itself is not moving left to right. So any one point of the rope, any one air molecule bounces around a little bit, but it actually doesn't move very far in distance. So that's sort of a visualization of the sound wave, or just a wave in general. And what you see is there's a given speed associated with that. So the speed of sound has been measured many times and comes out in physics units of about 344 meters per second, which is about 770 miles per hour. Well, Usain Bolt is often considered fastest man on Earth. And he could sprint the 100 meters at maybe about 23 miles per hour or something like that, which is actually pretty amazing when you think about a person being able to sprint that fast. Commercial jetliners fly near the speed of sound, but below the speed of sound, about 550 miles per hour. Depends on aircraft, depends on conditions, depends on how fast they're pushing their schedule. What's usually considered the fastest airplane in the world, SR-71 Blackbird, nice spy plane, goes over 2,000 miles per hour, faster than the speed of sound. So we know things can be pretty fast, but in fact, some things can be like really fast. So let me say, we also know the speed of light is over 600 million miles per hour. So that, if you know anything about Einstein and the speed of light, this is in some sense a cosmic sort of speed limit. We say nothing goes faster than the speed of light, but boy, is that fast. Now, one thing to keep in mind a little bit when I say these numbers is that the first three things I said over here are sort of people running, airplanes flying. Those are not waves. They're actually people or airplanes moving from point A to point B. Light, on the other hand, is a wave. Two quick consequences of having a speed of sound that's about 770 miles per hour. And since I mentioned Usain Bolt, let me talk just a little bit about the 100-meter sprint. And what happens is that there's, at the start of the race, there's a starter's pistol. And old days, the starter might stand by the inside lane or so. And there's actually a bit of a distance, about 10 meters or so, from the inside lane to the outside lane. People need a little bit of a distance apart in the different lanes. Turns out, if you calculate the speed of sound, it's very easy. Distance is speed times time. The time it takes for sound to travel from the starter's pistol at the inside lane to the runner on the outside lane is just distance divided by the speed of sound. If you plug the numbers into your calculator, you end up with about 0.03 seconds. It takes about 0.03 seconds, 3/100th of a second for the sound of a starter's pistol to go from the inside lane to the outside. Now, since sprints can be won by 100th of a second or so, this seems to provide sort of an unfair advantage to the guy on the inside, gets a little head start. Now, of course, the way we do sprints today is everyone has their own sort of pistol sound at their own starting block. So they all get the sound at the same time. And this is really something that you have to keep in mind when there is a speed of sound. So, now, we also know the sort of effect of the speed of sound if you've been in a large auditorium or maybe even a large stadium or so. You can see things, and then the sound comes just a little bit of a fraction later. Now, the second thing is there's also sort of an old trick for estimating how far away are you from a thunderstorm. So you're inside your house or inside a nice place that's nice and safe. You see a lightning bolt. You know what happens is you see a flash of light. And then, a second or two, a few seconds later, you hear the boom or the crack of thunder, something like that. What's going on there, of course, is there's one lightning bolt. In a storm, a few miles away or so, there's one lightning bolt. The light travels super fast. We could more or less pretend you see the light almost instantaneously. But the sound takes its sort of, relatively speaking, the sound takes its merry time getting to you. It takes about 770 miles per hour, which feels kind of fast, but actually does make the difference. What that means is you can make an estimate of how far away a thunderstorm is by measuring the time delay between seeing the flash of light and hearing the crack of thunder. If you work out the numbers, you take the time between the lightning, between seeing the light and hearing the thunder, and you divide by 3 to get an approximate distance in kilometers, or if you like miles, you divide by 5 to get an approximate distance in miles. So basically, you get a lightning flash like that, you count 1, 1,000, 2, 1,000. And so that storm is about 1 kilometer away or so from us. Now, if you see the lightning and hear the thunder exactly at the same time, make sure you take shelter, because then it's right on top of you. All right. Well, there's more to sound, of course, than just the speed of sound. We like to understand and characterize what is sound, what is noise, what is music. We want to understand the different types of sound. One way to do that is to actually take a look at sound. And the fun thing about having all these computers around is we can actually take a microphone, just record some noise. Well, there's different ways to create noise. One thing I can do, of course, is just sort of get some hissing of air over here. Good. Now, what you see is a pattern over here. It's a representation. It's a sort of a numerical representation of the sound waves that we're hearing. Good. That's you can hear all the little incidental noises. You can see when I started blowing the air is around this place over here. When I stopped is around the end of the wave over there. Let me zoom in a little bit. And you can look at the waveform. Closer, closer, closer. And it looks a little bit jagged. A little bit closer. Still looks kind of jagged. Let's zoom in even more. After a while, you can see the individual sort of oscillations of the wave. But what you notice is it's a sort of a jagged pattern like that. There's no obvious sort of nice pattern to it, shall we say. It sort of just bounces up and down a little bit, and it looks a little bit random. Now, that's the way the noise sounds to us. It sounds a little bit random. I want to contrast that to a note that we can play, say, on the piano. Good. And again, you can see a nice graphical representation of the sound from the piano. Let me just play it back first. But you see a pattern of sort of amplitude of the waves changing depending on starting the note and so on. Let's again zoom in a little bit. Messy, but let's zoom in a little bit more. And what you can notice is there's a bit of a pattern to it. There's much more of a pattern to this than there is to the hissing of the air noise. And in fact, you can see it's not perfect, but it sort of repeats. I can count, a peak over here, and it repeats another peak over here. It zigs a little bit, it repeats again over here and over here. So roughly I can highlight something like that. I've sort of blackened out an area, but it just shows you that I have a waveform from a tone or a note that sort of repeats over and over in a regular pattern. So we've learned that the difference between just sort of random noise and musical tones is this repetition idea, that there's a periodic or a repeating sort of pattern. So what really distinguishes musical tones from just random noise is the idea of a pitch. We hear a certain pitch associated with the sound. The pitch, in a way, is the frequency of the note, but the frequency, the pitch, all that comes because there's a regular repeating pattern of vibrations. When we hear pitches, when we hear tones, we are hearing a sort of a regular pattern of vibrations. So I want to show you that getting a pitch is just a regular pattern of vibrations. I can create a regular pattern of vibrations out of hissing air. And the way to do that is I have a fun thing over here. Let me turn this on. This is actually something like a circular saw blade with holes over here. Now, if I blow air through the holes, and if I turn the blade like that, what happens is the air goes through the hole, 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 and it repeats, hole, 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 hole. If I make it blow through enough times per second, I can actually get a tone out of it. So you see, the important thing is to have something that repeats. Repeats enough times per second that the disc is spinning reasonably fast. When you get this sort of repetitive sort of sound, that gives you a pitch, that gives you a tone. Well, these musical tones are caused by something that repeats, something that oscillates, something that vibrates. We know that can be created by vibrating strings, like guitars, string instruments. It can be created by vibrating air columns, trumpets, flutes, things like that. Turns out it can also vibrate drums by sort of beating on the drum head, something like that. They may not have a very recognizable pitch, but they still have sort of a drum head that's vibrating and vibrating the air. So let's see how we can characterize musical tones. If you ask sort of a musician when they play a note or something, how do they think about the characteristics of that sound? Well, there's the loudness, of course. How loud are you playing the note? There's the pitch. Am I playing in tune? Am I playing sharp or flat? What note on the scale am I playing? Timbre, the tone quality, what makes a guitar sound different than a trumpet? And then there's also sort of the duration, how long do I play the note? Now, as a physicist, I want to try to understand these qualities, sort of loudness, pitch, and so on. Turns out these are what are called perceptual properties of the sound. These are what I hear and how I interpret the sound. Do I hear it as very loud or very soft? Do I hear it as being a high pitch or a low pitch? Scientists will measure these properties, but they'll use sort of computers, microphones, instruments, and when they measure it, they measure what's called physical properties, such as sound intensity. If anyone has heard about, decibels, and then decibels is an example of a sound intensity level. You measure frequency, which is sort of a physical representation of the pitch, sort of waveform like I measured on a computer, and duration. How long is a note is the same, whether you measure it or you listen to it. So let me just say a few more words about the frequency of sound. The rate of repetition of something is how many cycles does it repeat per second. That is known as the frequency. And the standard thing is to measure frequency in hertz, cycles per second. Sometimes we also talk about the period of sound, the period of an oscillation. And the period is how many cycles, how many oscillations happen in 1 second. Now, how many oscillations per second, or how long does it take for something to repeat is the period. I got that backwards, but that's because there's a simple relation. If something takes 1/5 of a second to repeat, then it can oscillate 5 times a second. The frequency is 1 divided by the period. Period is 1 divided by the frequency. Good thing about this is I'm not actually going to make use of these equations. I just want to tell you that frequency and period of repetition are just very simply related to each other. So I want to just put some of these frequencies in perspective a little bit. So if I play the piano a little bit, the lowest note on the piano is about 27.5 hertz, and the highest note is a little bit over 4,000 hertz. So the lowest note over here, you think, is about 27.5. A little bit more complicated than that, but that's the basic idea. And we know the high note is a little bit over 4,000 hertz. So this is a sort of a musically useful range of frequencies. Well, although this is sort of a musically useful range of frequencies, it turns out that our human hearing can do a little bit better than that. And the sort of rule of thumb idea is that roughly we say we can hear from 20 hertz to 20 kilohertz. 20 kilohertz is 20,000 hertz. Although actually, if you actually test somebody's hearing, turns out usually we don't hear quite so high in the range. And this sort of, even reaching 17 or 18,000 hertz or so is generally for young people. Now, if I speak, as opposed to music, most of my voice information is being carried between sort of 300 to 3,000 hertz. Now I mentioned this idea that the high frequencies tend to be a little bit hard to hear. As we get older, our ears actually, it's biological, so I'm afraid it's just biological. Our ears tend to lose some sensitivity to higher pitched sounds. So I can plot roughly a chart over here of how good is our hearing depending on the frequency. So the frequency is on the horizontal axis, and I've plotted roughly just a musically useful sort of range of notes like that. And you can see, depending on age, that it falls off a little bit. Now, I can test your hearing a little bit because I can actually send sounds out over here. And so this is about 200 hertz. And let me crank it up a little bit. It gets a little bit obnoxious, so I won't do it too much. It's about 500 hertz over here. That's about 2,000, 3,000, 4,000. This is an obnoxious range. 5,000, 6,000. Well, let's jump up to, that's 10,000. 13,000 over here. 14,000. 16,000. And let me just kill it around that range over there. Now, some of those really obnoxious high-pitched tones, you can see, we can hear them, but we don't necessarily use them directly in music. They sort of show up in what's called overtones, but they are not necessarily that pleasing to listen to. So as I said, this is a typical sort of range of frequencies for speech, and the piano notes on the keyboard, if I put them on a chart, extend a little bit further than that. And this is just sort of to remind you, even as we get older, even as our hearing might fall off a little bit on the high frequencies, our ears still cover the range of music and speech generally very easily. So let's not get too worried about this sort of hearing loss as we get a little bit older. I've talked enough about sound. I want to sort of get back to the idea of music a little bit. And so the question is, how do we actually produce music? Well, we produce music with musical instruments. What are musical instruments? Basically anything you create can be considered a musical instrument. However, there are some general sort of ideas of instruments, and a very rough classification is to say, well, there's percussion instruments like drums or cymbals, marimba. I hit something and it makes some sound. There are wind instruments. I blow into something and it makes some sound. And then there's string instruments. I pluck a string or I bow a string and I make some sound. And so you see, I have sort of something to do with vibrating air, something to do with vibrating strings, something to do with hitting objects and making them sound. Key features of any musical instrument is we need to do several things. I need to sort of excite the sound. I need to be able to sort of produce the sound in the first place. So I can sort of pluck a string, hit a drum, blow a horn, something like that. Once I get a note started, I need something to vibrate or oscillate to sort of make my note, make my pitch, make my sound. I need some sort of a vibrating air column, a vibrating string, a vibrating drum head to sort of produce the tone. And then I need to end up coupling that vibration to the air. You need to hear it. You need to hear the sound that's vibrating. So I need to sort of couple the sound and radiate the sound out from the instrument basically to your ears. Let me demonstrate these principles of sort of exciting a sound and vibrating something and radiating the sound by considering the acoustic guitar. It's very easy to excite the sound just by plucking a string. So just plucking a string is a simple way to make the string start vibrating. Once the string vibrates, then the tension and the length of the string is designed in such a way that it vibrates at a certain pitch. And if the guitar is in tune, I even know what pitch it's supposed to vibrate at. The vibration of the string is basically what makes the note. Then, of course, the string on an acoustic guitar is connected through what's called the bridge over here and into the body of the guitar. And it's the body of the guitar that's vibrating that actually makes the sound come out in terms of sound waves that we can hear. So there's three parts over here. There's exciting the sound by plucking the string. There's the string itself, something that vibrates to make the pitch. And then there's the body of the guitar that sort of radiates the sound out to you. And so I want to demonstrate that it really is important to have a body or something. You can hear it resonates a little bit. It's sort of making a good coupling of the sound to the ear. So if I play something on the strings like that, it's not super loud, but you definitely can hear it. I want to contrast that to the electric guitar over here. Same set of strings. But if I pluck the strings, what do you hear? Not too much. You can listen quietly, you'll still hear something. Well, what's happening here is it's the same strings, it's the same sort of neck design and everything like that. It even has a bridge over here, but the body is different. This body is not designed to resonate and radiate the sound out to the air. It's designed for electric pickup and electronic amplification. So it's very important when you're producing sound to couple the sound to the air. Now, in a way, the electric guitar couples the sound to the air through a speaker. There's always something that couples the sound to the air. Here's another example of coupling the sound to the air, radiating it out. It's kind of cute. I have a spring over here, which if I squiggle the spring doesn't do too much. But it's coupled to a membrane. And the membrane is able to sort of push the air very easily. And when I put it together, I can get a good sound coming out of that. This is fun, sort of like thunder maker. Now, let me go into just a little bit more detail about how all that sort of stuff works. The guitar string can actually vibrate in a combination of modes, which we usually call natural modes. Let me draw sort of the first mode. This is perhaps the most obvious thing. If I pluck a string, you might imagine the string itself can vibrate up and down like that. And if I actually do a calculation, I find out it has a frequency. Since this is sort of basic mode, I call that the fundamental or the fundamental mode. And its frequency is given by some expression over here, which involves the length of the string, the tension of the string, T, and the mass of the string, mu. I won't say too much about that, except to note I'm dividing 1 divided by 2L in the frequency formula over here. L is the length of the string. F is the frequency. A longer string means I'm dividing by a bigger number. Longer strings have lower frequencies, lower pitches, all else being equal. That's why a string bass, an acoustic bass, has nice long strings. A violin has shorter strings. Now, of course, all 6 strings on a 6-string guitar have the same length, and yet they have different frequencies. And that's because you can also adjust the tension on the string and sort of the weight of the string. Like the low E string on the guitar is thicker, heavier than the high string on the guitar. So you can adjust the tension, mass, and length in various combinations, and music instrument makers have been doing that over the centuries to get the pleasing tones that they want. Now, the story is, of course, a little bit more complicated than that. It turns out I can also vibrate strings at different modes. If I vibrate it faster, higher frequency, I can get it to vibrate with sort of 2 lumps or 2 loops like that. And the frequency here is twice the fundamental frequency. I can vibrate a little bit faster with sort of 3 loops like that, 4, and it goes on forever. I'm just drawing the first 4 modes over here. When this happens, we speak of harmonics, second harmonic, third harmonic, fourth harmonic. And the vibration over here, the big part of the loop, the part where the string is moving the most, is usually called the antinode. Anti because it's the opposite of a node, and the node is, of course, where the string more or less does not vibrate. So this possibility of vibrations is very interesting because there's a pattern to it. There's an interesting pattern to it. And the pattern is, if I look at the frequencies, the fundamental has some frequency, let's call it F1. The next one is 2 times the fundamental frequency. The next one after that is 3 times the fundamental frequency, 4 times, and so on. Nice, simple integer ratios. This is known as a harmonic series. And if you're a musician, you can also call that an octave, 2-to-1 ratio. This is a 12th, which is an octave and a 5th. This one is 2 octaves, and so on. Now, I want to show you, not from the guitar string, which is not so easy to see, but from a demonstration over here, that I can really make strings vibrate with a different number of loops, different number of modes on them. So I have a string that we can set into vibration like that. And depending on the frequency I vibrate, I can get a different number of nodes. That's 3 over here. That's a better 3, actually. It's more like it. A little bit faster. 4. And as you can see, this is an antinode area because the string is sort of vibrating quite a bit. If I sort of touch the string over here, I stop it over here, I can stop the vibration, I can kill the vibration by sort of touching at an antinode area like that. A place like this is the node where the string, it might be vibrating just a little bit over here, but not too much. If I touch it over here, I might bother a little bit, but not too much. It doesn't really bother it too much, it still vibrates. So antinodes sort of kill the oscillation, nodes over here keep things vibrating like that. Now, fun thing about this is you can really start cranking it up. 5. 6, that's about all we go. So I want you to keep that in mind. Basically, when I play a guitar string, you're basically hearing the fundamental, or the first mode in this series over here. Now this fundamental mode likes to vibrate a lot in the middle. So if I put my finger exactly in the middle of the string and just touch it very lightly, just like I touched that string a little bit lightly, I can get rid of the fundamental mode. What do you hear? This is the regular string. And then I touch it here in the middle. It's an octave higher. That is mode number 2. This is known as harmonics, or harmonics on a guitar. So the regular strings, and by just touching lightly in the middle, whoops. Now actually I can do more harmonics on that if I'm careful. And so if you're a guitar player, you probably already know about that. And the physics behind that is just from the picture you see over here. By touching at the right places, you can kill some of the modes, leaving the higher harmonics left over to oscillate and to resonate. Well, I want to switch this a little bit. I want to talk about wind instruments, or vibrating air instruments. Turns out vibrating air inside a pipe has a very similar sort of pattern. You also have a fundamental mode, which is the way it likes to vibrate. This is sort of a pictorial representation. Remember, you can't actually see the air molecules, so this is a pictorial representation of the vibration inside an air pipe. This time there's a different sort of frequency relation, which is the speed of sound divided by twice the length of the pipe. So longer pipes, lower frequencies, shorter pipes, higher frequencies. The second mode, third mode, fourth mode, and so on. I can't really see the air vibrating like that, but I can see flames. And so I have a flame tube demonstration over here, which is a pipe over here. And what we do is we can fill the pipe with gas, and I can light it up. And what happens when you light it up, of course, is you get flames. But more than that, I can generate some sound. There we go. And I can generate some sound. I can make the air, or I can make the gas inside the pipe vibrate at different modes. And let's look at what happens to the flames. Flames are representing the pressure inside the pipe, basically. And the frequencies are a little bit obnoxious, but it's kind of fun. So it's 1, 2, 3, 4. Let's crank it a bit more. 1, 2, 3, 4, 5. One, two, three, 4, 5, 6. Let's see how much I can do. One, two, three, 4, 5, 6, 7. One, two, three, 4, 5, 6, 7, 8. And let me spare your ears after that. These type of musical instruments, there's always three sort of things. There's exciting the sound, there's vibrating the sound, there's radiating the sound. Well, for wind instruments, there's usually three different ways to excite the sound. Something like a flute. If you look closely at the flute, it has a mouth hole. It's just a hole like that. You blow not into the hole, you blow across the hole, and it sets up it excites the air, it sets up some vibration. That's sometimes called an air jet, because you're just like blowing air, basically. That's in contrast to, for example, reed instruments like the clarinet over here. If you zoom in on the mouthpiece, you'll find there's a little bit of a reed that when you blow, if you can actually play, as opposed to squeak, you can make the reed vibrate, and that sets the air into the vibrational motion. Then there's brass instruments, which are called brass because they're made out of brass. Well, actually, if you look at the brass instruments, there's a mouthpiece. And it looks like nothing is sort of vibrating, obviously, in the mouthpiece, except that you put your lips against it, and you sort of buzz your lips. The buzzing of your lips is what sets the air into vibration. For some people, that's also called a lip reed instrument. It's like a reed that vibrates, but it's your lips that are serving the purpose of the reed. Well, in terms of these type of wind instruments, I'm using wind to cover brasses in a more general sort of sense. Which one plays the loudest? Oh, I think the brass. And let's look at that a little bit. Well, there's a nice bell over here. I mean, there's different reasons, but there's also a bell over here, which is very effective at radiating the sound. This is what I mentioned. You need to have something that couples the vibrations to the sound waves in the air. And the trumpet or the brass instruments have this nice bell that flares out that does a very good job of coupling the sound. This is sort of a trumpet deconstructed. There's a mouthpiece over here. And so you use your lips to buzz to make some sort of a buzzing vibration, which sounds maybe like this. You can control your lips a little bit. I can't, but a good brass player can do that. That's how you get started with the vibrations. There's a tube, which serves as the air column. I can get the waves inside the tube. And if I connect the mouthpiece to the tube, I can sort of get things vibrating into the tube. You can hear it. It doesn't sound so pleasant, but it's not particularly noteworthy. The third aspect of the instrument is the bell, or the radiator, that sort of radiates the sound out to the air. And so I have a horn, which I can plug in. And you can see, actually, even if I bend the tube like that, make it look more like a bugle or something like that, I can still play a note. And so it doesn't really matter what shape the tube is. What does matter a little bit is the length of the tube, because that sets up sort of the fundamental frequency of air vibrations inside the tube. That's why a lot of these brass instruments are not just one long pipe like that, but because of being able to hold the instrument and everything like that, it bends around a little bit. So again, something like the trumpet over here has the tubes that goes in different directions. Well, there's something else you might notice for a trumpet. There's valves. And of course, the valves help us play different notes. I'll get back to that, but let me just sort of indicate there is a little bit of a puzzle if you've been paying attention to what I'm saying. The pictures I drew over here were the vibrating modes for a pipe that's open on both ends. Now, something like a flute, there's a mouth hole, which I blow through across. The hole is something like an open end of a pipe. The other end of the flute, if you look at it, where the sound comes out, is also open. That's sort of an open pipe. A trumpet, on the other hand, I put my lips against the mouthpiece. I'm basically sort of closing the air on one side. I'm blowing air through my mouth, but I'm basically using my lips to sort of close the side of the pipe. So a trumpet has one end that's open, where the air comes out, and the other end that's basically closed because my lips are sort of pushed up against the mouthpiece. So for a pipe that's open on both ends, remember we have what's called a harmonic series. For a trumpet that's closed on the left end, as I represented in the pipes over there, the picture is a little bit different. Closed on the left, open on the right end of the trumpet pipe like that. If you do a calculation, you find out the frequencies have a different sort of fundamental frequency, which is the speed of sound divided by 4 times the length of the pipe. But more important than that is the pattern of frequencies for a pipe that's closed on one end is a little bit different. In terms of the harmonic series, this is known as odd harmonics only. So the funny thing about the trumpet is, although you could think about it as sort of a closed-ended pipe, it actually plays all the harmonics just like an open pipe. In particular, I can play octaves on a trumpet. Without using valves, I can play octaves. Octaves are things that happen in open pipes, usually, and not closed pipes. So somehow you're able to play even harmonics on a trumpet, even though the pictures I drew for you for a closed-ended pipe doesn't have any even harmonics. Now, this is a very interesting phenomenon. What happens is there's more to a trumpet than just a pipe. Well, you look at a trumpet, it's more than just a pipe. If I started with a pipe, this might have sort of an odd harmonic series if I'm sort of closing the pipe on the left. But in fact, I don't just close it normally, I put a mouthpiece on the pipe. There's a certain shape to the mouthpiece which actually modifies the natural mode frequencies a little bit. There's also a bell that I stick on the other end of the pipe, and the way the bell flares out also shifts the frequencies around a little bit. And when I combine all these factors together, I basically end up with a harmonic series that can be played in a trumpet. Now, this is interesting because it's a little bit after the fact. People have played horns. People have made natural horns and bugles for hundreds of years, if not thousands of years. And they've been designed to play nice octaves, harmonics, and things like that, almost by trial and error, without mathematically or physically calculating, I need to have this type of bell, this type of mouthpiece. to make a nice harmonic series come out of a trumpet. And yet, nowadays, when we analyze musical instruments using our physics techniques, we find out that those master craftsmen of yore were really clever enough. They figured out the right type of design to make the most pleasing sounds out of these instruments. Let me just say, I gave you sort of a mathematics of a harmonic series. I told you all these different modes in the string, modes in the pipe, follow frequency, 2 frequency, 3 times frequency, 4 times frequency. The harmonic, that basically is the harmonic series, which I can play on the piano. You'll see that some of the notes actually do sound pleasing in this type of arrangement. Now, if you're a connoisseur, you knew I stopped there for a good reason, because after that, the harmonic series gets a little bit wacky. Anyway, standard notes you play on a trumpet, or a bugle, for example, with open, no valves. Follow these frequencies over here. There's another interesting story for any brass player that knows about pedal tones, which I won't get into, about not easily playing the fundamental in this harmonic series. So if I don't use any valves, I can just sort of blow into the different modes. Then you can get these notes over here. And this is how you can play simple melodies like bugle calls. Five notes plays that. Of course, we want to play more than just bugle calls. I mean, it would be very boring. It would be fun, but a little bit boring to only be able to play bugle call melodies on the trumpet. And so we need to have a better way to control the pitch of the notes that we play. And there's basically 4 different ways of doing that for these wind instruments. The obvious thing is the frequency or the pitch that I'm playing depends on the length of the pipe. Longer pipes play lower notes, shorter pipes play higher notes. So one way to play a whole scale of all the different types of notes is to have 1 pipe per note. And it might sound a little bit ridiculous, but this is exactly what we do for pipe organs. We can also adjust the effective length of the pipe by drilling holes in the pipe. So if I had a recorder, or even like a flute and clarinet with the holes, you see by using your fingers to cover or uncover the holes, I can effectively make the pipe longer or shorter because the air can come out of the holes. If I have more holes that are open, it makes the pipe effectively shorter and makes my notes play higher. So if you play the recorder, you know to play the lowest notes. Basically, you hold all your fingers down, all closed, and then you can play up the scale by sort of releasing your fingers one at a time, at least for a little bit. That effectively makes the pipe shorter, shorter, shorter. The notes go up the scale a little bit. Now, the trumpet has a clever design. It uses valves to change the length of the pipe. And so I have 3 valves, 1, 2, 3, like that. And the mechanism is very interesting. If I push down a valve, it directs the air through a little loop of pipe. Let me pull this one out here. Whoops. And basically, the valve controls the air. It adds an extra length of pipe whenever I push the valve down. If I add an extra length of pipe, makes the pipe longer, makes the note a little bit lower. So the interesting thing about the trumpet is when I push the valves down on the trumpet, I make the notes lower. I'm adding length of pipe to the, and then I make the note a little bit lower. Now, of course, there's another way to make the pipe longer without using valves, and that's a slide trombone. So I gave you some examples of wind instruments and how they produce the tones. I excite the sound. I have an air column that vibrates at a given resonant frequency, and I radiate the sound out of a bell or an opening. I said there are sort of 3 ways of vibrating the sound. I had what's called air jets, like blowing across a hole. I had reeds, like a clarinet, and I have brass instruments where I use my lips to start vibrating the air. Well, are there other ways to do it? Turns out there's another way to excite or vibrate the air in an air pipe or an air column. And it's really fun because you get to use fire. So this is like a big tube, big pipe. But I need a good size thing to excite a big size pipe. And the good size thing to excite the pipe is a nice good flame. There we go. Now, that's not necessarily claiming that that's very musically useful, but it's fun because somehow, if you actually look in the pipe, there's a little wire mesh in the bottom part of the pipe. What you're doing is you're heating up the wire mesh. You're using heat to sort of excite the sound. So it's a way of converting heat energy into sound energy. And you can hear the nice natural resonant frequency of that pipe. So basically, I didn't really emphasize the point, but when you think about playing music and musical instruments, playing different notes, what you're doing is actually resonating things. You're resonating air, you're resonating strings, you're resonating things at a given pitch, at a given sort of frequency to produce the note that you want. Now, in order to play nice music, you really want to control the resonances. You want to control them to not be too booming, to have the right frequencies, good things like that. I want to show you that you can also have uncontrolled resonances. Most objects do have a natural frequency. So if I had a wine glass over here, you've probably also seen the trick of taking your finger, I'm not going to do it, and sort of rubbing it like that, getting a nice sound out of it. That's the resonance of this wine glass over here. Well, if I resonate something, and I try to resonate it very loud, if I play a note at the same frequency over here, I can sort of excite the wine glass at this resonant frequency, and let's see what happens if we try to excite a wine glass at its frequency of resonance. So I have a wine glass over here, and I have a little speaker that can, it's been measured before to produce a little tone. Now I'm going to show you, I can adjust the pitch of the tone a little bit to resonate with the wine glass. And if you look at the curve in the middle of the screen, like that, you'll see the sort of sine wave pattern like that. If I adjust the pitch, what happens is I can adjust it to the resonance, and now once I'm on the resonance, I'll crank up the volume, make it oscillate, and then let's see what happens. So now I'm going to put on my ear protection. I highly suggest you close your ears, especially you guys that are close, and seriously sort of do that. And I'll give it a countdown, 3, 2, 1, and then crank it up. You ready? 3, 2, 1.
It's memorized.
It's a live version. Well, there it is. So just to wrap up, I hope I've given you some idea that physics and music is intertwined. And in a way, I don't want to sort of promote the idea, it's not just the physics that's hidden behind the music, but physics and music in an equal sort of level. So, all right, thank you.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.